So this will be our third class. And we're starting to move fast, right? First, I told you why welding is awesome, which I actually think. And it doesn't mean that you need to be a welder. You can do anything else. Then I said, okay, these are all the ways. No, what class is this? This is our fourth class. It said these are all our ways of putting two things together, right? Like from bolts to glue to, guess what, welding. And welding is a tiny thing in the world of putting things together. But I wanted you to know, so you would not be a monkey who knows only one trick. You'll be monkeys who know many tricks, all right? And then last Tuesday we said, all right, I'm shoving down your throat a dictionary, right? And I have no alternative because it's our language, right? Like we speak English here, and it wasn't our first language for many. We have to learn welding now, right? Like it's a new language. And in one lecture, I taught you the words of welding and the symbols of welding, right? We're moving fast. To give you an idea, if you go to SAIT or NATE, you'll spend a term learning what I gave you in half a lecture. I don't expect you to be as good as those people, but you'll be able to talk to those people because of that half lecture, all right? So please, because the lecture is somewhat lighthearted and so far you see very few formulas and everything, don't take it lightly, right? You're going to see in the exams I ask you to either write symbols or interpret symbols. And also you're going to see that the exam of every year is very similar to the exam of the previous year, which is good for you. But always there's something that increases a bit of the level of difficulty. So you guys are going to have the best welding class I ever taught. And, but hopefully not as good as the guys of the next year, right? It keeps continuous improvement. All right, let's talk shop now. And this class used to be only about the welding processes, right? And I'll start today, and I'll go fast too. Remember when I had all those acronyms, I said they might mean nothing to you right now, they're unpronounceable, but you'll own them and live and die by them soon. Okay, let's start with that. Of all joining, I reduced to welding. Of all welding, I'm reducing this to arc welding. Right, whatever arc welding is, but very soon you're going to know. And from arc welding, I'm going to divide it in a few things. One is non-consumable electrode. And what do I mean by that? Okay, I'll tell you, but not in the next slide. In the next slide, I'm going to show you something super cool. Have you seen this plane before? Isn't this cool, right? That's engineering. That's kind of crazy engineering. That's, I think, what you do after you drink a lot or perhaps you experience like some chemical effects, right? So the story is that in World War II, of course, there was a scarcity of aluminum because it was used for all the normal planes, right? And people said, okay, how else can we make airplanes? How about magnesium? Magnesium is a super bad idea for a number of reasons, including that magnesium is like what you would use to prevent corrosion everywhere else because the magnesium corrodes. Now you have a plane that is going to be all, what is it, a cathodic protection, right? Like very bad for corrosion. And while we're at it, trying crazy materials, how about if we put the propeller backwards and we don't put a tail? And so they actually built this plane. Now, why do I show you this crazy plane? It's because in addition to all the craziness they had, planes are riveted, as I mentioned to you, but they say, let's weld this plane. I really don't know what they were like drinking, smoking, or what. But they decided, let's weld it. But guess what? They had no way of welding this. They were barely, World War II, I showed you how people didn't even know how to weld ships. And now they wanted to weld planes, wanted to weld aluminum planes. All right, anyway, they figured it out. Of course, this plane didn't make it to the battlefront. Look at this other one. They thought, okay, the idea we still are not sure we're going to use in battle, let's take it to the next level and put jet engines. And how about if we put the pilot prone? And this is funny because they put like as if it is the Germans trying to ruin like a American bomber. But in reality, these are the Americans. And the plan was this plane had no machine gun, had no missiles, had no nothing. What you would do with the pilot going first head would break the tail of the other plane just by ramming into it. And of course, the pilot was assumed to survive and hopefully land. Well, let me tell you, not only they didn't build this plane, but at one point they realized that maybe having the pilot going head first into crashing into another plane is not a good idea. So there's another iteration of this plane in which the guy is sitting. Still a horrible idea. And still the plane is made of magnesium. But I guess if you're going to be suicidal, you don't care if it's going to corrode, right? So anyway, they needed to put this together. And what did they do? They invented what today we call TIG, right? And this was invented for welding this plane. Today, this is one of the essential technologies we use in this province. If you say TIG, everybody will know what you're talking about because everybody at NATE, SATE, and everywhere else, they live and die by TIG, right? And of course, I'm saying TIG, but I write GTAW. That is the official name, right? Some people say GTAW. Again, welding is full of mysteries. Who came up with this name and thought it was a good idea? But so this, if you go to SATE or NATE, this is among the last things they'll teach you because it's very difficult to do by hand. But it's the easiest to explain. So I decided to start here because it's easy to explain. So in this process, you have the electrode. You have the arc of arc welding. This J thing here is the arc. And the arc goes between two electrodes. Here's one electrode, and the other, in reality, we don't call it an electrode anymore, but that is the plate, right? And what else do you have? Remember when we talked that if you have the molten metal, if it is in contact with the oxygen of the atmosphere, it's going to end up looking like Swiss cheese, right? And I know this for experience. So you put inert gas. This K here, right, is the shielding gas, typically argon or helium and argon, but typically it's a pure inert gas or a combination of pure inert gases. Of course, to orient this shielding gas, you have what we would call the shielding cup. And here you have a photo. We're going to give you a demo of this. So you're going to see these things in action in our lab, and you can touch them and you can look at them. Unless there is some weird change towards the end of the class, I'm not planning on you welding on this because it's super frustrating. And all you do is you get frustrated, and then we need to start like cleaning these electrodes that get ruined. So this is called non-consumable because this electrode is not supposed to melt, right? Of course, if you use enough of it, it kind of wears out, but it doesn't melt. Now, if you want to add metal to it, you add metal from the side, right? Like, and you're going to see, I'm going to show you videos how the welders go with one hand with a TIG torch and the other bring the wire in. So gas tungsten arc welding, which I'm going to call TIG. So I already mentioned the protection from the melt. And the reason I put this in this sequence is because I'm going to show you a ton of welding processes. And each process has a way of protecting from the atmosphere that might be just like this or might be different. And this is an important aspect. The filler material, you can have no filler. So this would be an autogenous process, right, in which the rapprochement of the atoms is done by the melting of the base material itself. You don't add anything else. But you can have external, right? Could be the same as the base, right? Or very similar to the base and would be homogeneous, or could be different and would be heterogeneous. You can add filler, right? The way you would add this filler, right? It could be manual, right? And you make a little rod, and the welder goes with it's like a sewing machine. They goes with a TIG, melts a little bit of the plate, brings a little bit of wire, melts plate, wire, melt, and you see them working like this. Is quite awesome. That's manual. And it's a rod. And you're going to see when you name the electrodes, they are called ER70S, for example. The R stands for rod because you can use it for TIG. Or can be, I put automatic. Yeah, automatic. Here is, you can bring this from a machine, you push it. And if you just push the wire in, it's called a cold wire. But if you make this wire touch the weld pool, that now you know what the weld pool is, the molten metal there, the joule heating of another power source circulating current through this would heat up the wire, and it's called hot wire. Polarity. You're going to see lots of things about polarity, and this matters a lot. When I started my research in welding, I thought, who cares about polarity? But I'm going to prove you later on that polarity matters a lot. And typically in TIG, the polarity is electrode negative. There are good reasons for this, which I'll teach you later. But the electrode is negative, and you typically use constant current, not constant voltage. In constant current, the intensity of the arc, right? Remember that I mentioned the arc is very hot and also generates a jet that is about the same speed as a jet plane, right? This jet is about the same intensity if it is constant current. So you can be a little bit closer, a little bit farther from the weld, and you always have the same jet, right? Other things, in aluminum, sometimes you have AC, electrode positive, very, very seldom. It's only if you have no other way. But AC means alternate current or variable polarity. And you're going to see in the lab what happens with aluminum is that, you know, aluminum is not that aluminum doesn't get rusty and doesn't oxidize. Aluminum oxidizes. What happens is it has this protective oxide layer. Now, when you weld, what you weld is the metal, not the ceramic, the oxide layer, right? So the oxide layer is your enemy. So for reasons people don't really understand, but when you have what is negative in an electrode, in this case the electrode is positive but the plate would be negative, that breaks the oxide layer. Nobody knows exactly why. But if the electrode is positive, then the plate is negative, and you have what is called a cleaning effect in aluminum. In steel, you don't really need that, because steel doesn't have this really strong oxide layer on top, right? So you have different levels of AC, and you have different levels of cleaning of the aluminum, right? So you're going to see that difference between steel TIG welding and aluminum TIG welding. And as I talk about polarity, I'm leaving aside many details about the physics of plasmas, which we will discuss. For now, you have kind of to take me on faith what I'm telling you about these polarities. What characteristics that TIG has? You require high manual skills. I'll give you an example. In our lab, I'm the professor, but I didn't have the best car in the lab. The best car had one of the students in the lab who was a welder. So he would weld during the summer and be an engineering student for the rest of the year. The money he would make welding during the summer was good enough to buy an Audi, pay his mortgage, pay the mortgage for his mom, right, and go on fancy vacations, right? Isn't that crazy? And that's because he was a qualified TIG welder. That is the highest level. So when you make pressure vessels and those, you use a lot of TIG, and very few people are good enough. And those are paid like surgeons, right? Isn't that crazy? So you can make sophisticated welds with this. So the TIG is a little bit like a scalpel, right? You can do accurate operations. You can do small details, right? So if you're making a race car, you TIG welded. Parts of airplanes, TIG welded, right? Rocket engines, TIG welded. You can have a very high purity in here, and it is because everything is very controlled. You're not bringing a new wire, you don't have fluxes, you don't have any oxidating, you don't intentionally introduce any oxidating component here. You're going to see in other types of welding, you do. It has low fume generation, so it's quite like a it's quite like a clean and attention-oriented operation. You can make small welds. I put very small welds. We should take the very. Can make small welds. So it's good for thin sections, heat-sensitive materials. Remember when we talked about stainless steel? Right, and I said you don't want to overcook the stainless because it's going to sensitize, and it's not stainless anymore, and in addition, toughness is super bad. But TIG is a good way about it, right? Because it's so detailed, you would put less heat at the moment. What is the counterpart? It's a low deposition rate. So you want surgery? I want a scalpel. You want to take down a tree, you get a chainsaw. Well, this is not a chainsaw, right? You're not going to use TIG for like massive productions. Typically, everything I tell you here, I promise you there is a counterexample. But in general, TIG is not for large welds. Applications, typically shop welding. Can anybody remember, help me remember why this type of process, right? In this case, TIG is a shop type of process.
Because you don't want your expensive gas to blow away in the wind.
Right, right. You don't want the expensive gas to blow away. But let me tell you, even if the gas comes for free, it's bad, because the weld is going to be all like Swiss cheese as it gets in contact with the oxygen from the atmosphere, right? What do you use it in this province? A lot, the root pass of a weld. Remember see, I'm already using these words I told you have to memorize. At the weld, the bottom of a V groove, right? You have the root, and the root is relatively thin. So if you come like an animal with something that has lots of heat, you might ruin it. So with this, you have really good control of how you're going to attack that root, right? And so that is TIG. Yes. Oh, yep. Hold on. I forgot. I need to give you sound here. Now I'm going to show you a video that is descriptive of TIG. And I believe we have sound. I'm pretty sure we have sound somewhere, as promised here. All right. So,
gas tungsten arc welding uses a non-consumable tungsten electrode and externally supplied inert gas shielding. The most common shielding gases used are argon and helium, and mixtures of the two gases. All types of steels and most non-ferrous metals can be welded in all kinds of joints and positions. Depending on the application, workpieces can be welded without a filler metal or welded with a filler metal supplied separately to the joint.
That's a tiny
The
weld.
gas tungsten arc welding process employs either an alternating current or direct current power source, depending on the type of metal to be joined and its thickness. Some power sources provide pulsating direct current with variable frequency. These adjustments allow better control of the molten weld metal when welding thin sections and when welding in other than the flat position.
All right, there you go, like an introduction. This is a video typically aimed for the trades, but at least you get to see how it was used. By the way, when you see the people in our province, they look a lot more skilled. They were just putting the torch against the you don't do that. Our guys are like really sophisticated. Okay, so let me show you some videos we took in our lab of TIG welding. So let's see, here this is 150 amps in argon. I'm going to put them all here, here, and here. So these are videos. They look like photos, right? Because nothing is moving. But in this one, you can see how it is. Here in this one, you get to see how it changes. So remember when we talked about constant current or constant voltage, and then I mentioned advanced waveforms, because now that the things are like a computer, you can tell it pulse high here and low there, high and low. So in this case, we're just pulsing high and low, high and low. So when the current is high, the arc swells up because it's taking all this energy through. When the current is low, it gets smaller, right? I'll tell you more about pulsing in a second. You see this other one that looks ghostly? This is in helium, right? Pure helium. That's very uncommon. Sometimes you would use helium, but there are pros and there are cons. But if anything, helium is very expensive and non-renewable. Argon comes from the air, right? And you get to see how the arc looks quite a bit different, right? The physics of the helium has significant differences with argon, and we're trying to understand those right now. The physics of the plasma are not so well understood. Why would you want to pulse? For many reasons. One of those is aesthetic. So there are some types of welds in which people like to see what they call a stack of dimes. Imagine you have a stack of dimes and you tilt it and goes like scales of a fish. Some people like that finish. So if you pulse it that way, you get that finish. The other reason is sometimes you want to have good penetration, but not too much heat. So every time you pulse, it's as if you dig a little bit, and then when you don't pulse, you're not digging, right? So when you pulse, it would be a sequence of spot welds, pretty much. Right? Those are decisions that are made depending on considerations of aesthetics or heat input or preference. In this class, you're going to see many of the aspects that help you make those decisions, although very often they're kind of mysterious the way they are taken. All right. In TIG, there is something called the gas lens, and it's interesting, but we have one Mickey here, I believe, right? Who's that? You, okay, welcome. It's two. No, Mitch is there too. Three, Louis. Oh, come on. Okay, so we can come out the closet then, huh? It's, so, remember I mentioned we want to, molten metal and oxygen of the air is bad, so you have to separate them. One of the ways is you put an inert gas, for example, argon or helium, whatever, right? Now, when you're blowing a gas, as you guys know, the flow can be laminar or turbulent. And if you want it laminar, typically related to slow velocities. But if you have slow velocities, it means you have little gas. So some people say, oh, I'm going to give it a really good shielding and open up the tap, right? And they're blowing argon like crazy, spending money like crazy. And guess what? It goes from laminar to turbulent. And now you're worse than before and more expensive than before because you can do everything worse if you don't know what you're doing. Now, smart people realized that if you put something called a gas lens that has nothing to do with a lens, I don't know why they call it a lens, right? That is kind of a little mesh that they put inside the torch. It creates a laminar flow. So it comes out of the torch already laminar and gives you this longer stretch in which you're going to have laminar flow and good shielding. Right? Without the gas lens, you can take the gas lens and you're still welding. You think, what is this for? What happens is that you cannot separate the torch very much, and your chances of entraining air from as you shield it is higher, right? All these things were things people were discovering as they were going. If you see a wind tunnel, you're going to see something very similar to a gas lens. They don't call it that. I don't know what they call it. But you're going to see that if you put your airplane here and the air is blowing this way, they have like typically some sort of a mesh to make the air very laminar as it reaches the model, the scale model and the wind tunnel. Same thing here. So if I were to ask you, we seem to have a problem with shielding. We're talking about TIG and we have a problem with shielding. Should we use more gas? Right? Maybe, maybe not, but the answer is not clearly yes. Right? Because if you have no gas, probably you have a problem of shielding and you should have more gas. But if you have too much gas, maybe your problem of shielding is that you have too much gas. You should not add more because you're only going to make it worse. Right? All these things are things that can take days and many thousands of dollars in delays and problem with the products. But it's not going to happen to you guys. You're going to be awesome. Okay. And by the way, they don't teach you all this when you learn to weld properly. They just teach you to weld. But this type of thing is for good welding engineers to know. Okay, remember what I mentioned? You can add the wire by hand, as you saw in the video, or automatically. So you feed the wire from a feeder. One of these techniques is called hot wire. And this is a photo of the patent. And funny enough, this guy is still around, right? This looks like Victorian era, right? But this guy is around. He's a guy who, Gus Mans, until not long ago, he was in charge of the AWS welding handbook. And what did he invent? Here you have your TIG torch as usual, right? And here you have the wire they are adding. It's coming out of a spool, and the wire comes in. Now, what is not shown all too clearly here is you see that says power supply and power supply. This power supply is a power supply for TIG. Everybody has one of those because otherwise you cannot do TIG. But let's say we have 2 power supplies now. Right? We have power supplies like this in the lab. We have 2 of those. So you have an extra power supply, and now the current, right, would go through this wire from the workpiece, the plate, through this stretch of wire. You see this little line here? This is super important. And then this other part here is called the contact tip and goes to a power supply. All these are big, beefy cables. Right? This is a big, beefy piece of copper. This is just your everyday welding wire. Now, the current here has resistance, so it has Joule heating, right? And this Joule heating, if you time it just right, and we had a guy doing a PhD just on that. If you time it just right, it's going to come relatively cold out of here, and as the current circulates, it's going to reach right melting point as it touches the weld pool. Now, here's a paradox. Hot wire. If I use hot wire in a weld, what do you think? I'm going to have a hotter weld or a colder weld? Right? Yeah, of course, everybody would think hotter, but in reality, you get a colder weld. And this is why is the reason of this paradox. If I add the wire by hand, right, or with cold wire, I need to melt this wire. So I need to have a bigger arc, right? So I have an excess of energy that is aimed to melt the wire, right? So that's what most people would do, and has some amount of heat into the plate. And as we talked, the heat into the plate will result in different cooling rates, different hardnesses, whether it's coursing or sensitization, right? All those things. But if you have a hot wire, you don't need that extra energy because you're putting exactly what you need and not more, just what you need because of Joule heating. So you're putting this large amount of metal right at the melting point. So in conclusion, you use hot wire to get a colder weld. Who knew, right? Again, this might throw lots of people. They are quite difficult to set up. But I think this is an amazing technology that is quite underutilized because you can put lots of metal without paying the price of the heat of all that metal. All right, and then you have to have 2 power supplies, but typically that's not the biggest deal. All right, let me show you a video of this process in action. So this is a video from our lab. This is our TIG electrode, right? This is made out of tungsten. Tungsten has a very high melting point and also has a property of being thermionic. Now, here you don't see it all too well, but you see this ghostly image here, right? This is the hot wire coming in. And you know it's hot wire. You see how it's already kind of molten as it is coming in? It's not coming in straight and strong. It's coming in already molten because you have the current moving. I'm going to show you one more thing, and it should blow your mind. Look at the arc, yeah? Oh. Oh. You see? I want to know what's going on in there. What's going on? Okay, who said that? Okay, you say polarity. What do you mean by what do you mean by polarity?
Like you have like 2 power sources, right?
Yes.
Match them so you don't make a short circuit.
Right, but so to be clear, you said polarity, but in both cases, the electrode here is negative, the plate here is positive, right? And that did not change the polarity. Here, right, let me think. If this, I believe, here the wire is negative and the plate is positive. No, the wire is positive. Here the wire is positive and relative to the plate, right? But the polarity did not change. What changed? But you're onto something. So we have what is called arc blow, and it's an electromagnetic interaction. So it is such a pity you guys didn't have electromagnetics, although a few of you did, right? So this is a story. This arc is fine, right? But here we have another electrical current. So this is not going to have much of an effect on something that is so strong. But this guy has a current, and this current generates a magnetic field. And the magnetic field interacts with this current and generates a force. Right? And it happens that this is a pulsed power source. It's not variable polarity, but it's pulsed. So what it increases, the current is going like that, I believe. So when you have this current interacting with this current, right? The two opposite currents repel each other, right? And so here the current is coming like this, and there is coming like that, right? They repel each other. So that's called arc blow. Here has not been a problem, but very often, if your plate is magnetized or something like that, it's going to move your arc. And the welder has a really hard time, because if they want to weld this one point and the magnetic fields move their arc, they cannot do it, right? Very interesting. Okay, true or false? Gas tungsten arc welding uses a consumable electrode. False, thank you guys very much. Of course. Unless you're like me and you change the polarity. If the electrode was positive, let me tell you, you melt the electrode. But you shouldn't. All right. Let me discuss a close cousin from TIG that is called plasma transfer arc welding, or plasma arc welding, right? There are different types of plasma. Plasma transfer arc welding means that the arc is transferred between the electrode and the plate. So what is similar to TIG here? You see this tungsten electrode here? That's the same a TIG electrode, and you're going to see in our machine in the lab. We're going to give you a demo. Here's the plate. Same thing, and we have a weld pool, a deposit, and an arc. So far, so good. What is different? The torch is different. You see this part here? What we have now, at least 2 gas streams, right? We used to have 1 gas, that was the shielding gas. Now the shielding gas comes from here, same as before. So the TIG, the tungsten electrode, you know, the shielding cup, you know. We're fine. This is now a nozzle. And what they did is they encased the electrode in a nozzle, and they blow this secondary gas, right? This, what do we call it? This is the primary, what they call the primary gas, not secondary, the primary gas. So as you blow this primary gas at a pressure, you make an arc that is moving at, that is constricted. Right? If you remember the arcs that you saw in the videos about TIG, they were like a bell, right? Like a Liberty bell, right? Like big. But in plasma, because you're having this primary gas blowing very strongly here, you constrict the arc, and the arc becomes even more of a scalpel, right? Now it becomes so narrow that it can compete with laser, right? It can be very, very focused, right? Now, what we do in this province, in addition of this plasma process, is we have a third field flow of gas that is called the carrier gas. And this carrier gas can bring powders, and we can then deposit powders and do additive manufacturing, or put corrosion protection coatings, or wear protection coatings, right? So you have a third flow of gas. And here, in the nozzle, you would have either 2, 4, or very many holes, and the gas comes out of here, gets molten in the arc, falls here, and you have a process in which you have a filler metal, right? But you have no wires or anything like that. You're going to see this in action. Okay, protection of the melt, again, is a shielding gas, typically argon. Sometimes they put a little bit of hydrogen. We're going to see that hydrogen gives you a hot arc, and also is a reducing gas. On the other hand, hydrogen is typically very bad for steel. So if you're going to do it, you have to know what you're doing, so you don't get on the wrong side of things and end up with hydrogen cracking. So the filler metal, typically, it is heterogeneous powders, right? Mixtures of nickel and tungsten carbide. But the base is steel, right? But you put on this carbon steel, nickel and tungsten carbide, right? You can use things that are like corrosion protection powders, right? Typically, you do this only in the flat position. Anybody remembers Thank you. Anybody remembers what we call the flat position? Okay, what is flat position? Is this?
1F, 1G.
Yeah, the 1F or 1G, right? When you're doing overlays, right, or cladding, you have no fillet and you have no groove. I don't know, but it's position 1, right? Flat. You seldom do it in other orientations, right? And the reason is you put such large deposits that they would fall, right? So this is typically constrained to the flat position. Typically, you have no filler, and that would be plasma arc welding, and that would be autogenous, right? And that would be a welding process. You can use this same technique since it is like such a concentrated heat source. You can use it for cutting, right? Plasma cutting. We have a plasma cutter in the lab, which we should demo, right, Mitch? Did we plan on showing the plasma cutter?
We can show it.
But we should, right now that I remember. Yeah, you should. We have everything, so you have to take advantage and see everything and learn. Polarity. All right. Polarity is typically electrode negative. Does it make sense? I have a tungsten electrode, right? If I were to revert the polarity, I'll melt the electrode. Right? So typically you do it in electrode negative constant current. Characteristics, very similar to TIG, but more concentrated, can create a keyhole. Remember, we also mentioned briefly what a keyhole was when we were talking about the terms. Remember also when we talked about the relationship between intensity of the heat source and the human response time, and how we can do oxy-fuel welding by hand. We can do MIG and TIG by hand, but we cannot do laser and electron beam by hand, right? Plasma welding is the first one that you cannot do by hand, right? It's right at the limit in which you cannot do a good weld, right? It's too small, moves too fast, just a bit more than you could. And of course, I'm sure if you try, you could in some conditions. But typically, you don't do this by hand because of the intensity of the heat source. So this goes back to what we discussed in our second lecture. Because you can make smaller beads, right? Sometimes you put lots of material, but you put it flat, right? But you can make details, even smaller details than with TIG, right? If I make a very small detail, what do you think? I'm going to cool down fast or slow? Fast, right? So some materials are heat sensitive. For example, mixtures of nickel and tungsten carbide. Tungsten carbide is a ceramic. You mix it with nickel. You melt the nickel. You don't want to melt the tungsten carbide. That's fine. But the tungsten carbide might want to dissolve in the nickel, right? Like the same way a sugar cube dissolves in your coffee, right? So now, if it cools down very quickly, it dissolves very little, right? So for that reason, in this province and many other places in the world, you use PTA very much for this type of heat-sensitive, wear-resistant overlays, right? You can do things with high purity, has a relatively low deposition rate. We're going to show you in our lab, we have a huge torch that says, oh, this is large deposition rate. But when we learn about submerged arc welding, you're going to realize, no, that's Mickey Mouse. The other one is a really large deposition rate, but it's not as pure and not fast cooling rate. Applications, wear resistant, wear protection overlays for mining, wear protection overlays for oil and gas, often nickel, tungsten carbide, but other wear and corrosion resistant overlays. You were at Apollo, right? This is a reason they use lasers, because that's the next step. And you did lots of these nickel tungsten carbide, right? Yeah. So let me show you
In plasma arc welding,
a video here.
metal coalescence is produced by a constricted arc made up of a high-velocity stream of ionized gas called a plasma. In most plasma arc welding operations, the plasma jet is generated by heating the orifice gas in the torch polenum chamber to a plasma and forcing the plasma to exit through a constricting nozzle or orifice. Partial shielding is obtained from the plasma and is supplemented by an auxiliary shielding gas. Auxiliary shielding gases used include argon, helium, or mixtures of argon with hydrogen or helium. Because of the constricted arc, the heat energy of the plasma stream is concentrated and extremely intense. This permits deep penetration, narrow welds, and rapid welding speeds with good arc stability. Workpieces can be joined with or without filler metal. Plasma arc welding can be used to join most ferrous and non-ferrous metals, including extremely thin materials such as foils. Plasma arc welding equipment cost is high, however, so the process is often limited in its application.
Question, why you mentioned that you can weld thin foils with plasma? Why? Why plasma yes and TIG no?
There could be a few reasons.
Good answer. You sound like a materials person now.
With the temperature control is better and your arc is much constricted and targeted, I guess. It's
Okay.
easier to get a cleaner weld and not break the material while doing it.
Okay, that is true. But overall, this type of concentrated heat sources, what they do, as you said, is because it's concentrated, it's small. If you want to weld something that is thin, you want the heat source to be not much different than the thickness of what you're welding, right? Because one reason is, if you're going to be melting this much, the two parts are not going to touch each other ever. But the other reason is such a small heat source can give you a small heat input. Remember, joules per kilojoules per centimeter, right? And something thin is very difficult to dissipate the heat, because the heat, very little goes to the air. Most of the heat wants to go through the metal, but if it is very thin, it's really a choke point, right? So the heat accumulates, right? We're going to have equations for all that, and you're going to see this exactly, right? Okay, so let me show you our PTA in the lab. This is a torch. This is a plate. This is 10,000 frames per second, very high speed, right? And this is at 4,000 frames per second, right? What you see falling is the powders I mentioned, right? The nickel and tungsten carbide that will create the wear protection overlay. Oil sands would not be profitable if we did not use this, because if we don't use this, our machines would spend more time in shutdown than producing. Right, and it was at Suncor when they first started to realize that these wear protection overlays would make their machines have enough uptime to be profitable, right? This is incredible, right? So here you have the powders falling. You see how they bounce, right? This is what is called the catchment. You throw the powders, right? Some powders will stick, some powders will not stick. They are very expensive. I forgot the number, but I'll find out, and you'll see it's very expensive. And everything that is not in the weld is something you paid for, and that is going to go to a trash can. Right? It's very difficult to recycle because these powders have a high purity. Right? There are ways of recycling them, but you really have to know what you're doing. Right? For the most part, people trash it. Question to you: what do you think is the condition for bouncing off? Why would something stick or bounce off?
Could have to do with velocity.
Velocity, I believe velocity plays a role, but I think it's minor. Right? What do you think?
Particle size and cooling rate.
Particle size would be right.
It's not hard enough to attach, because if it's too small, it'll dissipate its heat faster.
Yeah, could be. I haven't done that study, but in general, all these powders are getting heated up there. But what we have seen from our experience in lasers, which I believe applies to this, you see all the powders falling, and then you have the molten metal. If they fall on the solid, no chance to stick. They're going to bounce off. Molten metal on solid metal, Nothing happens. That would be spatter. Now, molten metal powders falling on the melt, they have a high chance to stay. But it's not 100% still, for reasons that, again, we don't understand. We have even written a paper and we have videos showing. Sometimes the powders come, and instead of staying, the molten bit of metal staying in the molten weld pool, bounces off. I don't know. You see, there are topics for masters and PhDs as you wish. Yeah.
So the mechanism by which these powders are getting stuck onto the piece that you're welding is because they're getting submerged in the molten metal?
Yes, yes.
And that's the only way the powder's sticking to the...
If it doesn't fall on the melt, it doesn't count. If it falls on the melt, likely counts. Right? But issues, as you said, velocity of particle size, those matter because you have to penetrate the surface tension barrier. Right? All right, true or false? It's true, it's true. PTA has such concentrated heat that it competes with laser for many applications. Now, there are things lasers can do, PTA cannot do. But when you have a laser, typically you have such a streamlined operation, clean, good engineers, you know what you're doing. So very often people would use lasers for things you could do with PTA. But the reason is you have your customer service, you have your supply chain that you can trust, right? But I believe PTA is something that deserves attention. All right, this is for non-consumables. I will talk next about consumable electrodes, but do you guys have any questions or comments so far? Who has seen TIG in action? Who's aware of having seen TIG? You did? Okay. Did you try, any of you tried it by hand? No? You did? How good are you? When I was a professor in Colorado, we decided to create a bicycle building club. And I'm the professor of welding and students. One of the students started to make bicycles like overnight. It was crazy. He was making bicycles for their father-in-law and their friends and neighbors. It was amazing, right? I have the samples I tried to do. I don't make bicycles. I talk about welding, but it's very, very difficult. Like
uncontrollable, like the moment the arc is produced, like you have to be like right there and like focused on where you're going.
Yeah.
Otherwise, you can just go in the wrong direction.
Yeah. But you say it's uncontrollable. Yeah. What happens is you wanted to be an engineer. Some guys love it. It's like being a musician. Like, shh. But I don't know. They have a robot for hand. I don't know how they do it. If you hold a TIG torch, which if you join the lab, you'll have a chance to do it. But we don't plan to do it for everybody in the class. You're going to see that it's really, really difficult. Any of you have been trying to apply silicone in the bathroom or something? No? Have you tried to do that? That's difficult already. This is next level. I was doing that last weekend, and another job I shouldn't take. Okay, so consumable electrode. So I think we're in good time. Okay. Consumable electrode. So now I'm going to talk about things like MIG. And I say MIG, but I write GMAW. Now, here's a subtlety. GMAW is one thing. MIG would be GMAW. But for Europeans, MIG means gas metal arc welding. And you have to know that, right? And in the notes I uploaded, there is all these acronyms explained. It used to be called metal inert gas, right? Gas metal arc welding, metal inert gas, when you use argon. Now, you might use CO2 that is not inert. So they would call it metal active gas, right? So Europeans still call it MIG and MAG, and they care very much. So if you say MIG, if I would say GMAW with CO2, no problem. But because I don't say GMAW, I say MIG with CO2, the Europeans say, that's nonsense, right? Like, that's MAG. Fine, whatever, sue me, right? But you should know this, right? I'm going to say MIG, but in reality I mean gas metal arc welding, right? And I never say MAG, but maybe I should. But so look at this. This drawing is much the same as the drawing for TIG. We have a plate. We have an arc. We have an electrode. We have a shielding cup or a nozzle, right? In the case of the MIG, you call it a nozzle. In TIG, you call it a shielding cup. But it's same thing, right? So what is different now? The difference is this electrode now is melting, right? In TIG, the idea is you don't melt it. And if you melt it, you're up for a good talk with your supervisor. But in this case, you want to melt the electrode. So if you melt the electrode, eventually you're going to run out of electrode, right? So you start feeding the electrode is a wire, and you start feeding the wire. Remember when we talked about the cast and helix of the spool, all those things? I was talking about this wire that is all rolled up. And you start to unspool the wire. Now, because I need electricity to feed the arc, right? I have a sliding contact. The wire keeps coming in, right? And somehow I need to bring electricity to the wire. This sliding electrical contact is called the contact tip. The contact tip costs about $1, and it's one of the central pieces of technology of MIG. Now, very funny, nobody wants to pay more than $1, but a whole lot of problems in MIG come from the contact tip. And when companies are designing their equipment, they care a lot about how is the contact tip going to wear, right? How is the contact tip going to maintain a constant voltage, and lots of things. So this is much the same as before. I want to bring up three important things. Here's the arc, and I didn't mark it here. Anybody remembers what this distance would be called? Say? Arc length. Yeah, right. You are right. I didn't mark it here, but you have to know that's the arc length, right? And then there's another one. The contact tip to workpiece distance. CTWD. Again, another of those acronyms. I don't know who comes up with this, but contact tip to workpiece distance. That is from the contact tip to the workpiece. This matters because you can measure it, right? This is easy. If you have an automated process, you come with calipers, you measure from here to here. You can do lots of things. You know that. You can set it. If you have a robot, that's what the robot controls. This part of the robot controls. But we have an arc length, and then we have something else. This wire sticking out, this is called the electrode extension, and it's very, very important, right? So, and this line here in reality is not so sharp because I didn't mark if it is above the melting droplet or below the melting droplet. And else is, I still don't know how to call it, right? And there's big debate in the community about what is arc length and what is electrode extension. But for now, I made it fuzzy enough, and I'll be okay with you if you give me an equally fuzzy definition. Now, question to you. I have taught you nothing about plasma, nothing, right? But if I keep the same contact tip to workpiece distance, because I put my MIG torch in a machine, and I increase the voltage, right? What do you think how do you think these lengths are going to change? So the machine use higher voltage. Say?
Shorter.
What is shorter? I agree with you. Why?
Because the power you consume is more, and the chance to heat the wire faster, right? So that the extraction is
You're onto something, but I said lower voltage, and you say the power is higher.
lower voltage. So it would
I said lower voltage, higher voltage. Okay, good. Sorry. So, but he's right. Now, the reason would happen is right. Most of the resistance is here happens here in the plasma because it's a gas. The metal has little resistance. So if you say, I'll show you later. I want higher voltage. Typically, what the machine does is whoop, give you a longer arc. right? And we can calculate that, right? And this is important to know because it has many practical consequences. If I have a longer arc, do you think I'm going to have a broader weld or a narrower weld? What do you think? Broader, right? It's like a flashlight. Like you step back and it gives you broader, right? And this we're talking here that for you might seem like small steps. We're talking about things that are level 3 of inspectors, like people who have very advanced practical knowledge. Okay, so protection of the melt. TIG, plasma, we use typically pure argon. But now in MIG, we use other blends. There are good reasons for this. One reason is if I put anything that is oxidizing with a tungsten, I'm going to ruin my tungsten, right? So that's bad. But in the case of MIG, I'm melting the electrode constantly, so it doesn't matter if I were to oxidize my electrode. The electrode keeps melting, so my problem is in the weld, but not anymore in the electrode. And now I can play games. For example, I can use pure CO2. Guess what? CO2 is a lot cheaper than argon, right? Actually, we pay to get rid of CO2, and then you go and buy it. Who knew, right? It's interesting. So you can have blends with different gases. Gases like hydrogen could be, or CF4, that is a crazy gas in which you put small amounts, and the fluorine will react with the hydrogen and suck up the hydrogen to give you low hydrogen welds. You can use helium. And also you can use mixtures of argon and oxygen, or argon and CO2. Why would you have those mixtures? The reason is that the arc in tungsten is pretty well defined because tungsten has special properties for the arc. It's called thermionic emission. Whatever it is, we'll discuss it later. But steel, aluminum don't have those things. So the arc is quite unstable. But if I have a little bit of oxidation, the arc stabilizes, right? And this is somewhat related to this issue of cleaning. I mentioned to you that when the plate is negative, right, we clean it, and we do that in aluminum. But in steel, right, when the electrode is negative, if I put a little bit of oxide, the arc gets stable. Filler material. You have I put automatic wire feed, but people call it semi-automatic, right? Because you have the torch in your hand, but the wire comes automatically, so it's semi-automatic. That's the way people call it. If the wire is solid, right, is gas metal arc welding or MIG. But also, now you can play games. How about if instead of having a solid wire, I make a tube, right? And we have the technology of making the tubes, and the tube can be steel. And inside I can put lots of chromium, and all of a sudden I'm making you a stainless consumable without having cast like 50 tons of stainless steel, right? So many advantages. In that case, now it's called metal core arc welding. But it's the same thing, right? It's just that the wire, which looks just the same, is a little tube, a very thin tube, instead of being solid. Now, how about if instead of metal powders, I put some ceramic powders to create this layer of insulation from atmosphere, right? That would be called flux core arc welding, and has all these fluxes I mentioned in one of the previous classes. This doesn't mean water closet, this is tungsten carbide. People put that too, right? And that's very, very cutting edge technology, right? And maybe we can replace PTAW. Now, question, is based on what I told you about PTAW, that is very low, very precise heat control, right? And in this case, you would have MIG, right? What would you prefer, to do the PTA, the tungsten carbide, in PTA or in MIG, and why? Anybody remembers what the problem with the tungsten carbide was?
The mixing with the...
It wants to dissolve, right? So you do PTA, low heat input. In this case, if you do this type of technology, you dissolve a lot of the carbides, and it's very bad, right? So you can do it, but it would be a last resort. polarity now is typically electrode positive. Remember, TIG was electrode negative, and now this is electrode positive, for good reasons, right? And also, if you remember, TIG was constant current, so I would have always an arc of the same intensity. But in MIG, we have constant voltage, right? Why do you think we might want to run constant voltage? If I have constant voltage,
To control the arc.
say?
To control the arc.
Right. If the constant voltage is constant, I have the torch in my hand, and I can come in and out and do things that as a human you have like little variations, but the arc is always the same length, right? You would not want to come in and out and all of a sudden the wire starts sticking out, right? I have managed to do that myself despite the constant voltage. But proper welders don't have that problem, right? So think how different these things are and how different the machines are. In the past, the machines had a completely different electronics because some electronics were for giving you a constant current or a current source, or the others to give you constant voltage. Right today, the machines, because they're a computer that happens to give you electricity, in reality are all constant current machines, but they fake it to make you think it's constant voltage, or can be constant current, or can be anything in between. Right now, the machines are
have to pass a certain threshold current to make the transfer happen?
Yes.
It happens much faster.
Why? Yes, by what you,
obviously,
yes.
if the current's really high.
yes, but why?
But why? Does it have to do with capillary? Not capillary.
Well, capillary plays a role, actually, but capillary opposes the detachment. So what pushes the detachment? If I have smaller droplets, I have higher capillary. So here I have higher forces for detaching than there. What force would be stronger now, here than there? Who said that? Electromagnetic. So in welding, current typically goes associated with electromagnetic forces, right? And isn't that funny? You don't need to know how to read and write to be a good welder. But to understand welding, we're talking about more things than you have been taught, right? So electromagnetics matter a lot. So there is something called the pinch force, which we're going to see later. But the bottom line is this force that tends to squeeze things, that is called the pinch force, goes with the square of the current. So at low currents, pinch force is low. It just is a drippy faucet. At high currents, you start to squirt it. But it's kind of magical, right? There's nothing mechanically squirting it. It's just these electromagnetic forces, right? Okay, so in MIG we have this is the same graph as than before, but here we have where we would divide this. Welding machines tend to run here. So a commercial welding machines, for example, those called synergic, they combine. In MIG, you said, and please take a note of this because I didn't put it in the slides. In MIG, you give a voltage, but you don't give a current. You give a wire feed speed. You say, how much wire do you want to melt? Okay, so many meters per minute or so many inches per minute, right? And it burns that. So you said two things. You can set two things, but typically machines will try to think and say, you wanted low power, right? You go here to a short circuit at low current. You want more power. You go to spray. Typically, you want to avoid globular. Globular, it gives you spatter. It's not as directional. See, when this says about directionality, it's because this thing is like a laser beam, like squirting this. These things, the droplets are falling more or less whatever they want. I talked about power. You guys know that voltage times current is power, right? So the voltage times current constant would be this hyperbolas that we didn't draw. This would mean low power here, higher power, and here you'd have lots of watts, right? Voltage times current. Here is a lot of watts. Here is very few watts, right? Which one would you use for a thin plate? Left or right? Right? This is what you use for thin plate. This is what you use when you're making filler passes in a thick pipe, right? But isn't this awesome? Because this is very practical in the end. But you're saying the practical things coming from understanding, right? That's pretty cool. All right, so we have a few more minutes, and I want to go over these metal transfer mechanisms. So let's start with globular, right? We already mentioned that it's like a drippy faucet in which you have the big droplet that detaches by its own weight. There is a definition that says globular is when the droplet is bigger than the wire. You know what? I don't care about that definition. Typically, it's true. But what really matters is that the physics of detachment is by weight, right? Which typically happens to be the droplet bigger than the wire, right? And electromagnetics are relatively small. The droplets not always fall actually, so sometimes go to the left or to the right, and this is a problem because a welder needs to put the metal right in a place and the droplet goes elsewhere. So you also have high spatter because sometimes the droplets fall out, happens at relatively low currents. For reasons nobody really understands. I don't. Nobody really can give you a straight answer. But if you use lots of CO2, you're going to have globular transfer, no matter what you do. You go to high currents, still globular transfer. So now it's a funny trade-off. I want to use a cheap gas such as CO2, I'm going to end up with a pretty crappy metal transfer mechanism. Sometimes it's okay, sometimes it's not okay. But now you start thinking, oh, can I deal with lots of spatter? Maybe you're making a weld that is so big that you don't care, right? Sometimes it matters. So CO2, high amounts of CO2, and by high amounts I mean amounts above 25% CO2 will give you globular transfer. The welding equipment in this case is relatively inexpensive, right? Because it's not a high quality metal transfer method. So these limitations, high spatter, operators don't like it, and very often if the welder doesn't like it, you know what, you have a problem. You end up with like a big weld bead, right? It's not as neat and clean as spray transfer. Spray transfer, and I'm calling this streaming spray. You saw an intermediate thing called projected spray. So you have globular until the globular is so small that it's kind of a mini globular, right? That's called projected spray. At that point, the electromagnetic forces are pinching enough to eject the droplet, right? And then when the electromagnetic forces are huge, you just pinch a long tail, and that is called streaming spray. So I mean, streaming spray happens at high currents. You need mostly argon gas. I would say less than 20% argon. You have small droplets at 5 frequency. Now, if you have high current, right, you have lots of power to melt the base metal. But also, these droplets are coming fast, and they are acting as like they're going straight to the bottom, like cannonballing here very quick, and they give you this type of penetration. So if you look here, this would be what a typical penetration is in globular. Here is a typical penetration in spray transfer. So just think of this. If you wanted this penetration, you needed to melt all this, you needed to put lots of heat. But here, if you wanted this penetration, you put a little bit less heat, right? You save from melting all this part here and melting all this part there, right? So you can have this high penetration with more efficiency. Good for welding thick materials without causing much problems. High deposition rate, good electrode efficiency, so low spatter, good weld appearance. The operators like it, right? It tends to be one process that would give you good fusion. Sometimes the big droplets here would fall, but they don't really melt the sidewall, the V-groove, and you have the effect that is called lack of fusion that shows up in X-rays. You don't see it with your eyes because you see the cap passes only. Okay, so it's 3:20. I'm going to stop here and pick up on this on Tuesday.